We are continuing in the revision for all of the HSC topics you've been looking at in Extension 2, and it's still funny to me that there's just the 5 of them, right? So we started at complex numbers, we then did proof, we went through vectors, further integration, and then we finished up with mechanics. So those are the 5 topics you need to master, and being that we had a look at 3D vectors and proof last week, I thought, yeah, let's go back to integration. It's been a little while, and we didn't get to assess it in your previous task. So you can have a look here, and just to refresh your memory, you can see this this notation of the capital I for integral, and that sort of subscript of an m. This is an indicator that you're dealing with a recurrence relation or a reduction formula, different names for the same thing. So this is kind of our warm-up question, though I've said that a few times this afternoon, and I just want to point out one of the reasons why I'm giving you this question is because it is question 8 of a previous HSC when there used to be only 8 questions in the Extension 2 paper. And as a consequence, like it's tough. It's so tough that less than a quarter of the state were able to get this question with full marks. Maybe there was an element of fatigue there, like you've gotten to the end of question 8 and your brain is just fried. But there are some twists and turns in here. So it's 2:12 at the moment. I'd like to give you guys about 5 minutes. Even if you know exactly what to do, there's still a fair bit of work to go through, and it is a proof question, right? So you cannot skip any of your logic there. You have to really show you know what you're doing in your integration by parts and so on. So I'm going to call it at 2:18. If you have not done, if you're not finished by 2:18, then please just pop a message to Mrs. Lees or I and say, I need more time. But otherwise, if you are ready, give us an indication. Some of you have been having a go at this question for a little bit, and I can give you a bit of a heads up about what the next question will be by a direct message so we don't spoil it for everyone. But being that some people only just entered on time, I'll pop myself back on mute. I'll leave the question on screen, so you don't need to take a screenshot or anything like that. And give us an indication one way or the other if you are done or if you need more time. That's all from me for the next few minutes. Good luck. Okay, I call time. Hopefully that is enough for those of you who feel like you knew what you were doing, and also wasn't too long for those of you who are just like, I'm beating my head against a brick wall, so let me help you out. When we have a look at this question, what makes it challenging? Well, there's a couple of things. Firstly, being that it's a recurrence relation, which we kind of already signaled from the beginning, we know that integration by parts is almost certainly going to be the way that comes out. And the first thing that is challenging about this is that it's not exactly a straightforward integration by parts. You're pretty used to saying, oh, choose one of these as u and one of them is dv, and then off you go. But here, owing to the fact that these are algebraic, right? You actually have to do a little bit of manipulation to make the integration by parts work nicely anyway, and not be a complete dog's breakfast. That's the first thing. And then the second thing is, you can see it's a second order recurrence relation. You've got this mth integral with an x to the power of m, and then you've got this m minus 2th integral, which means you're going to have an x to the m minus 2 up here. And so you've got to sort of, you might think, oh, there's 2 steps that I have to go through. So in order to try and make clear how we actually get this relationship and get the proof, the first thing I want to do is notice that, whoopsie daisy, because I'm going to be looking for an I m minus 2, I think it is going to be helpful for us to say, well, what is I of m minus 2? So off to the side here, before I've even begun constructing my proof, I'm going to say, well, what is that equal to if I just take the definition of I m, because that will help me. It's a bit like in when you're proving a trigonometric identity, you get given the final result and you're like, oh, I'm thinking like, where is there a sec x that will appear, or where's the tan squared? You know that's your destination, so that guides the simplification that you do. So what is I of m minus 2? The only place that m appears in this definite integral is just up here in this power, right? X to the power of m. So I'm going to substitute that for an m minus 2. And then when I have a look at the rest of the integrand, it's independent of m. So I can somewhat, well, I'm not going to ignore it, but I'm not going to make any changes to it, yeah? So it's going to be x squared minus 1 to the power of 5 dx. So I'm going to file that away for later. I'm hoping that I'm going to go through integration by parts. That term, or that whole expression there on the right hand side, is going to appear somewhere, and then I can do some rearrangement and algebraic manipulation to get to the required result. All right, so let's make a start on actually dealing with this integral. Now, like I said before, the first thing that is non-trivial about this, and maybe this is why some of you are stuck and you're like, oh, I couldn't even progress very far, is that choosing either x to the m or x squared minus 1 to the 5, choosing either of them as u or dv, neither of them are really set up nicely to actually end up on the result that you want. So we actually have to do a teeny bit of manipulation to help us, right? Now, what I would suggest is when you think about, I've mentioned to you, I like to think about which one should be dv, right? Because you know you're going to integrate that. So what's a thing that's easy to integrate? Either of these are relatively simple to integrate, but if you've tried this, you've found that it's not going to get towards this, because when you integrate x to the m, you get x to the m plus 1 on m plus 1. So you're going further away from I m minus 2. You're getting I of m plus 1 and some other stuff, right? So that's why this is not a good candidate for dv. It's just as easy to integrate. It just doesn't get you toward this recurrence relation. So that's the first thing I want to signal. The second thing is when you have a look at this term here, right? This x squared minus 1 to the 5, it by comparison looks terrible to integrate. You're like, gross, like I have to use reverse chain rule. But then when you think about how to use reverse chain rule, you need the inside derivative to appear, and there is no inside derivative. It would be 2x in this case, right? But I've sort of flagged this earlier, right? Even though 2x does not appear, something very much like it is still accessible nearby, right? It's not a 2x, but there's a whole bunch of x's in that x to the m term. There's m of them. So I can just borrow one out of there. It's not the same as 2x, but it's only off by a constant coefficient. So I think that's good enough for me. So therefore, here's what I'm going to write. I'm going to say, let's break apart that x to the m into an x to the m minus 1 and an x, right? Which looks not simpler, but it will help us with the integration by parts that's about to ensue. I'm then going to get x squared minus 1 to the 5 dx. There's no change there. And now I'm ready to choose what will be my u and what will be my dv, right? As I kind of flagged earlier, I'm going to suggest that rather than choosing the x to the m minus 1 term as dv, which integrates and goes away from, I want to go down, not up, I'm going to choose that as u. So that's x to the m minus 1. And then when you think about differentiating that, it's pretty straightforward, right? So you pull the power out the front. So this is du on dx is going to be m minus 1, x to the m minus 2. And that's your first indication that you're like, ooh, m minus 2, that's promising, right? I need one of those, yeah? So that's sort of already a good sign for us. Let's do the rest of the integration of my parts. So I'm going to get my dv on dx. Now remember what I did was I pulled out this x so that I can do reverse chain rule on this whole term nice and simply, right? So what am I going to get here? I've got x outside of x squared minus 1 on to the power of 5. Which I guess you could say, whoopsie daisy, I guess you could say is like, I'm going to put a half out the front and then multiply by a 2 in there. Because now look at that. That's like perfectly in reverse chain rule setup. I've got the f dash, the 2x, as compared to the f, which is x squared minus 1. So that's pretty much ready to go. When I integrate this to get my v, what is going to happen? Well, I'm going to raise the power. So that's going to give me x squared minus 1 to the power of 6. I'm going to divide through by that 2x because that was the inside derivative. And then I'm going to divide by the new power. Now, I've already got a half out the front. So when you divide a half by the new power, which is 6, you're going to get 1 over 12. So there is my v having integrated. Okay?